So now let's take a look at how we can formulate our optimization problems so that it's defined correctly, because in some cases, this might not always be straightforward. Ideally, we want our correctly set up optimization problem to return to us only one single unique solution. Now, what does it mean? Let's consider this very simple maximization problem where we want to maximize f of x, our objective function, being x1 plus 2x2. And this is actually a linear problem because we're only looking at x1 and 2x2. Now, this objective function can be plotted in such a contour plot. So remember from previously, we said that we use red to blue color scale, where redder means higher value because it signifies hotter, and colder values or bluer regions signify that they have a lower objective value. So in here, you can see, because we're looking at an optimization problem, regions over here would have higher values, and similarly, regions over there will have lower values. So our solution would be somewhere here, or tend to the reddest region. And let's say now we actually have three constraints for this problem, where we have G1, G2, and G3, and these are all inequality constraints. So for example, G1 is 2x1 plus x2 minus 20 less than or equal to 0. G2 is minus 4x1 plus 5x2 minus 10 less than or equal to 0. And G3 is x1 minus 2x2 minus 2 less than or equal to 0. If we toggle these constraints on, you can see G1 is this shaded area, G2 is this shaded area, and G3 is this shaded area over here. So if you remember previously, we said that the shaded regions are invisible regions, so we can't have our solution anywhere in this shaded area. We can only find our solution, feasible ones, over here in the unshaded region. So let's take 5 seconds and see if you can identify the optimal solution satisfying these three constraints that has the maximum value of our objective function here. Remember that we want to focus on areas or points that have the redder color in them. Using this line of thought, see if you can identify the constraint maximum point in this problem here. Okay, so if your answer to this problem is this point, then congratulations, you're correct. The reason why this point is the maximum point is because this is the only possible point within this shaded region that has the reddest color. So that's why it has the highest value, and that's why it's a maximum point. So if we look at the constraints over here, we can see that the maximum point actually touches the two constraints. And we call the constraints that a solution touches on the active constraint. So here G1 and G2, which are these two regions, would actually be active constraints. And G3 over here, because the solution doesn't lie in anywhere in this constraint, so it's an inactive constraint. An active inequality constraint can be effectively replaced by its equality constraint version. For example, G1 here can be replaced by H1 without changing any result because it's still being on the constraint line. And similarly for G2 as well, we can effectively use H2 and take away G2, which then becomes just two lines. And this will be equivalent because we're saying that the point has to be on these two constraints, and this will effectively be equivalent. Now for the inactive constraint, we can actually just remove it altogether because it doesn't affect any of our solution. So in here, we're saying that the constraint where the optimal point lies on is called an active constraint, and inactive constraints can be practically removed without any effects on the optimal solution. Now, once we've removed the inequality constraints and replaced them using equality constraints, we can see that there's actually no other feasible points other than this particular solution. This is because we are requiring that the solution has to be on this line as well as this line. So the only feasible point will be their intersection, right? Rather than an optimization problem, this is more like solving for the solution because there's only one feasible point, and that feasible point by extension is also naturally or automatically the optimal point. However, this is still theoretically a correctly set up optimization problem, although it might not be as meaningful because you aren't really choosing or selecting any other feasible points. You're simply saying that the only solution there is also the optimal solution. And indeed, if we have two equality or active constraints in a two-dimensional problem, a problem with two design variables, we will have nothing to optimize. There will only be one single solution. If we now add one more constraint to this problem, let's say we have h1 and h2, and we add another constraint called h3, given by x1 minus 2x2 minus 2 equals to 0, you see that we can no longer say this is the solution because the point must lie on this constraint, this line, and this constraint, and also this constraint as well. In fact, there is no feasible solution at all for this problem because there are simply too many constraints and we are restricting the design space too much that there is no feasible solution. So the entire problem is infeasible. It's not a problem because we cannot actually get any feasible solution, let alone optimal ones. So the principle behind how to set up a feasible optimization problem, to ensure the problem is feasible, we first have to have inequality constraints together provide a feasible region. But more importantly, the number of active constraints must be less than or equal to the number of design variables. So previously, when we just have two constraints, we can still have one single solution, although that is automatically a feasible point as well as the optimal point. But nonetheless, it is still theoretically correctly defined. But once we have one more constraint in this 2D problem, so that in total we have three constraints, there will no longer be any feasible point for us to explore. However, in here, we're talking about independent and active constraints. Now, let's say if we have h4 instead of h3. So h4 looks something like this, the line in the middle, given by minus 2x1 plus 6x2 minus 30. Now, this constraint is actually not an independent constraint. You can also see graphically or intuitively from here, because it crosses the two lines, you can still find an optimal point that automatically satisfies these three lines. And the mathematical way of explaining this phenomenon is that this constraint over here, h4, is not an independent constraint because it can be written as the sum of h1 and h2. So if you combine h1 and h2 together, 2x1 minus 4x1 will become minus 2x1, and x2 plus 5x2 will be 6x2, and minus 20 minus 10 will be minus 30. So h4 is not independent of h1 and h2. In fact, they are related by the fact that h4 is simply h1 plus h2. So because this is not an independent constraint, we can remove it because it's just sum of the two. In here, although there are three constraints, but for independent ones, there are actually only two. So we still have a feasible solution, which is this point over here. Now, if we think about another extreme condition where we actually end up with infinite number of solutions instead of one single solution or no solution, this would happen if you have a constraint that is a linear combination of the objective function. You can imagine it graphically as something like this constraint here, h5. If you can see this gray line over here, it overlaps the contour line exactly. So it means that this constraint, whatever x1 and x2 I choose, it will be at the same value because this is a contour line. If you remember from the previous visualization video, we say that all of the points on the same contour line share the same objective value. So this means that this constraint requires that the solution to be a point on this line, but all of them share the same objective value. So there isn't really an optimal one. All of them are solutions. All of them are feasible, and all of them are no better or no worse than each other. So again, this is another extreme of setting up an infeasible or ill-defined optimization problem where you actually end up with an infinite number of solutions. This one example shows that when the contour line and the constraint actually overlaps, this will give no good solution because all of them are solutions. So this is also conditions or situations that you want to avoid. So you want to set up your constraints correctly to avoid being as dependent on your objective function or being another linear combination of other constraints. And this might sound very difficult to understand. When can I avoid these situations? But if you visualize them, you can very quickly tell just by inspecting it graphically why this is such a case, why when we have 3 constraints, for example, then we won't have a solution. You can see if we have more than 3, then it will be even worse because you can't find a point that satisfies it being on all of the lines simultaneously. So graphically, you can understand it this way. And similarly for H5, if you have a constraint that lies on the contour line, then obviously it won't give you any meaningful result because all of the points have the same objective value. So you can't really judge which one is worse or which one is better. And this is a very important area in optimization problems because only by setting up your optimization problem correctly will you be able to end up with effectively one unique solution that makes sense, that is meaningful. And that also resonates again with our first flowchart about how optimization problems are run. If your problem has been ill-defined, then you might end up with solutions that are not meaningful. That will prompt you back to the very first stage of revising your optimization problem definition. So this is how we can use graphical techniques to help us in understanding whether our optimization problem has been set up correctly. And that also emphasizes the importance of exploring your design space before you actually commit to running an optimization problem, because it allows you to spot problems like this